Welcome to the first video of a new chapter. This is data chapter, and in this chapter we are going to discuss about how is information translated to the system a computer understands. Okay, so that is universal translator fundamentals of binary. So we know just a computer works with binary. So see how does everything work. Okay, the physical reality of our computer system is that it is made up of metal, silicon and copper traces. It operates solely on electricity. Okay, and only understand physical voltage, current flowing or current not flowing somewhere. Okay, so that is how our hardware is. And in the virtual world, our data is just kind of complex logic and applications that our softwares, high definition graphics and colors, text, audio, character. So we have just gotten different things. The question is, how does electricity understand Shakespeare? Okay, that is, or how does this kind of pictures and audios and text is understood by this hardware or by our processor? Okay, so that is a question we are going to answer in this unit. See, the processor contains billions of microscopic transistors, and each transistor is in the state of on or off, 1 or 0. Okay, on simply it means it transmits electric current, and off it means it does not transmit electric current. Okay, so that is the main thing. And because the processor's physical circuit only have two physical states, okay, on or off, transmits electric current or does not transmit electric current, the entire computer must operate using a base 2 or binary mathematical system. So every information, every data that you have, it must be changed to binary. Now see, in real world we work with analog signals, okay, but in computer we just work with digital signals. And what is the difference between them? Okay, analog signals like sound waves or light waves or things like that, okay, signals that are continuously variable and contains an infinite range of values. So here see, every part of this can be just a different value, okay, and it's just continuous. So it has continuous range, okay. Traditional sound waves, that is the example for that. Very high precision but highly susceptible to noise. So for example, data is here, a little bit noise can just change that, okay, and that is the data will be lost here if we just work with analog. So it needs highly expensive equipment to be transferred, okay. So noise does not damage it or things like that. Then we just come to digital signals, okay. Digital signals, a system composed of separate, discrete and fixed operational states. So we have gotten separate operational states. It's not continuous that here as well we have a value, just lower as well we have a value, here as well we don't have that, okay. So they are just completely separate. We have gotten a value here, another value here, so whatever we just have, okay. So here it ignores voltage drift and only looks to high or low extremes. For example, if data is here, if the voltage is here as well, processor will just consider it to be just in this position, okay, because it does not understand this part. Or if it just here as well, it will just simply consider it to be here. So we have gotten separate and discrete operational states, okay. Then it is high resistant to noise. For example, if our data is here, a little bit of noise can just bring it lower or higher, but again we will just it is nearer to this level, so simply it will be just the same level, okay. And binary is the most common two-state digital implementation, okay. So we've got only two states. See how data is represented. The first one, okay, the universal code. To a processor, there is no physical difference between sound, graphics and text. Everything is simply processed as streams of binary bits. So picture is also saved as zeros and ones, sound is also saved as zeros and one, text is also saved as zeros and ones and things like that, okay. And software content, what is just context, okay, program instructions dictate interpretation. See, the exact same bit sequence 1010 can just be an integer, it can be a sound pitch, it can be a text, or it can be just a symbol, okay, or just anything. But the programs or the software just simply dictates the processor how to interpret that. Should it just change it to a number, a color, sound, pitch, or what. Okay, so we have gotten bit patterns. Individual bits are combined into larger structural patterns to represent increasingly complex data structures like characters or image. See, in one bit we can store only one or a zero, and with that we can just have only two states. But for our data, we need to have just kind of complex sequences of zeros and one. So what we do, we just combine, or we do not have only two states. Okay, we have gotten many states, for example, in sound or in letters, in numbers. Okay, we have gotten just different numbers. We do not have only two. So as a solution for that problem, we combine many bits and just calculate or just take in account the pattern created by those bits, okay, for different things. So we will just discuss further about them in the next chapter slides. So see here, we want to just kind of talk about combining bits and key formula. See, if we have gotten only one bit, in one bit we can store one or 10. So for one bit we have gotten two combinations, two values. Okay, it can be just one or it can be zero. If we have gotten two bits, in two bits we can store four different combinations. Both of them can be one. One can be one, the other zero. The first one can be zero, the next one can be one, and 0 0. So we have gotten these four different combinations that can be stored in 2 bits. Okay, and if we have gotten 3 bits, in 3 bits we can have 8 different combinations. Okay, all of them can be 1, then 1 1 0 1 0 1 1 0 0, and just we have gotten just different combinations. Okay, so combining bits will allow us to have just different combinations and store complex data or different values inside a computer. Okay, so for different combinations, or the number of combinations according to the number of bits, we have gotten this formula: 2 to the power of n. 2 to the power of 1, okay, 2 to the power of 1 is 2, so we have gotten two combinations. 2 to the power of 2 bits, okay, it is just 4, so we have gotten 4 combinations. If we have gotten 3 bits, so 2 to the power of 3 will be 8, so we have gotten 8 different combinations. Okay, so that is the formula: 2 to the power of n, where n is the number of bits. Then multiplication principle: each bit doubles the number of possible combinations. So with 2 we have gotten 4. Add 1 bit there, it will be 8. Add another bit there, it will be 16. Okay, so we can just have 16 different combinations. And byte power, what is a byte? The 8 bits are called 1 byte. Okay, and that is just a standard number of bytes to change different values. Okay, which just results in 256 unique sequences or unique combinations. Okay, so 8 bit bytes that results in being able to store 256 different combinations or sequences. See, we have gotten 1 bit. So for 1 bit, 2 to the power of 1, 2 combinations. Okay, example for this, where can we use it? For monochrome graphics, only black and white. Okay, so 1 is, for example, white and 0 is black. We can just do that. 2 bits, so 2 to the power of 2, we will have 4 combinations. Example for that is early retro graphics. Okay, we have gotten only four different levels of gray. Okay, then 4 bits Nibble, 2 to the power of 4 is 16. So we can have 16 different colors. Okay, and that is a kind of 16 color palette we can just use. And 8 bits, which is just a byte, 2 to the power of 8 will be 256. So we can have 256 different combinations. Okay, and example for that is extended ASCII characters. So we will discuss about them in detail. Okay, so we can just store 256 different combinations in 8 bits or 1 byte. Okay, so 1 bit, 2 bits, 1 bit or 4 bits or 1 nibble, and 8 bits or 1 byte. Now see, the same sequence can be just a letter. Right now that is 65 as integer. If we just want to store the integer 65 as well inside computer, we will store the same thing. If we want to store a inside computer as well, we will store the same thing. If we want to just kind of have a color or just a sound, a specific volume sound, it can just be any one of them. Okay, so core insight is the processor does not inherently know what the binary pattern represents. Is it number? Is it text? Is it color? Is it sound wave? Okay, the program instructions dictate how the ones and zeros are interpreted. So if you are just using any photo viewer or photo editing, that's just mostly colors. Okay, if you are just working with audios, then yeah, that will be just changed to a sound pitch. Okay, so something like that. See here just an example about pictures. We will just study in the future videos in depth. But right now, for example, this is a monochrome picture where we have gotten only white and black pixels. Okay, it can be stored like this. See, one is just white and zero is black. So see, we have gotten three whites, so one, 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 then one black, four whites, and then zero, one black, then three whites. Okay, and we can just have all of them the same. You can pause the video and you can just watch it. Okay, so this image can be just saved inside computer like this. So each pixel here, because we have gotten only two colors, so we can use one bit to represent one color. Okay, so pixel, the smallest single point of color in a graphic image. Color depth. What is color depth? The number of bits used to encode the color of each pixel. Here, color depth is 1. If we just use 4 bits for each one of them, it means 16 different colors can be represented. Then yeah, the color depth will be 4. Okay, so something like that. In metadata, additional data is stored alongside the image that shows the width, height, color depth, or things like that. Okay, information required to reconstruct the raw binary. Okay, so one, this will be stored. Metadata before this, yeah, you will just have some other information that will give information to the software or to the program that yeah, this image is having a width of this many pixels, height of this many pixels, and color depth is, for example, 2 pixels or 4 pixels or 8 pixels, or color depth is 2 bits, 4 bits, or 8 bits, something like that. Okay, we will just study them in detail in the future. Right now, just introduction to binary. Let's just have some exam survival toolkit. Okay, some golden advices for or some golden advice for your exams. Okay, the golden rule: no calculator is allowed. So all binary conversions and arithmetic must be done mentally or via written working out on the exam paper. Okay, and for that you need to just kind of memorize this numbers. Okay, 1, 2, 4, 8, 16, 32, 64, 128. Okay, so that is just not very difficult. Each value is double of the previous value. Okay, you will just use this to answer different questions. Okay, you can just kind of change binary to decimal or decimal to binary using this. Okay, and the other thing, okay, on the exam days, be careful about the command words. Okay, for example, if inside the question it said that calculate, so always show your working calculated. Okay, always show your working. How did you just kind of get to the answer? So these steps. Okay, marks are awarded for the correct process even if the final arithmetic is slightly off. And construct an expression, do not solve it. Okay, if in the paper they just tell you construct an expression for something like this, do not solve it. Just write a mathematical formula with the numbers plugged in. Calculating the final answer wastes time and risks error, and in these questions that will not be scored as well, even if you just get them correct. So here we have got an example. For example, there is a diagram that shows a black and white image consisting of 36 pixels on the paper. Okay, there is just something like that. Explain why 32 bits are needed to represent the pixels in the image. So see here, the examiner here tells you explain. That is one tip. Explain requires a logical reason, not just a statement. Okay, and just reason it, give reasons behind that. And the other tip here is, okay, 2 marks. If it has 2 marks, then you have to just kind of give 2 distinct points. See, for answering this question, we will just have something like this. The image is black and white, so there are only 2 possible colors. Therefore, a color depth of only 1 bit is needed per pixel. 2 to the power of 1 is equal to 2, so 1 bit. That is 1 score. And because there are 36 pixels in total, each requires 1 bit of data, the total storage required is 36 bits. Okay, so that is just your second mark. If you just write one of them, you will have 1 mark only there. Okay, and the next question, okay, an analog audio file is recorded in mono for 2.5 minutes with a sample rate of 44 1100 hertz and a bit depth of 16 bits. Question. Construct an expression to calculate the size of the file produced. Express your answer in bytes. So you do not need to do the calculation. So see, construct an expression. Simply, it means you do not need to do calculation. Now, for answering this question, you will need some information from the next videos, okay? So here, if you do not understand that, no problem. But as you can see, the final answer that we have here is just an expression, okay? A formula. We just do not need to calculate this. So yeah, that is the hertz multiplied by the bit depth multiplied by mono, okay? We have just gotten one file there, and 2.5 minutes multiplied by 60, okay, and divided by 8, that is just kind of changing into byte. If you do not understand it in this video, no problem, okay? But in your exam, if you are just told to construct an expression, you need to stop here. You do not need to just try to solve the math problem, okay? And to finalize things, okay, here we have gotten mastering binary is mastering the universal translator of modern computers, because every device just works on binary, okay? Every piece of software you will ever use lives within the math of the transistors, okay? So here, see, abstraction that we have studied in unit 1, we have got an abstraction here as well, okay? See, layer 1 hardware, silicon transistors and physical voltage we have here, okay? So that is just our hardware. Then binary architecture that works with zeros and ones, so digital states of ones and zeros, okay? We will just change that transmitting current or not transmitting colors to ones and zeros. So that is just a simple level of abstraction, okay? Then data structures, bytes, pixels, ASCII, sound samples that we will just study in this class, okay? We are just combining those bits to give them some meaning, okay? And in layer 4, software and UI, that will be just interpretation level, okay? Which is just games, browser, and apps. So as you just go higher, you will have a higher level of abstraction. It means just you will be focused on the things that, yeah, will work for you. You need to just kind of work on them. You do not need to kind of change, care about how your sound wave or command or text is changed to binary, and how does the processor work with that, okay? So you do not need to think about that. So that is just abstraction, okay? That can be just question in your exams. And that's it for this video. Wish you all the best, okay? Come back to learn more in the next videos. Wish you all the best. Good luck and goodbye.